This is example 13.1 from Discovering Design with Chemistry, and now we are in the chapter all about heat. Our first problem says a 500-gram block of copper starts out at 51.2 degrees Celsius and cools to room temperature, which is 25 degrees Celsius. How much heat did it lose? So our special equation that helps us understand heat is the one that starts with a Q. That Q tells us how much heat we gained or lost. And so we just need all the pieces so that we can put it in there. So we need the mass, that's the M. We have mass, they told us that at the beginning. We need C, that's given at the end of the problem. That's our specific heat capacity for copper. And then we just need the change in temperature. So we have the temperature that it started out as, and we have the temperature it ended up as. And so if we take those two numbers and put it in the change of temperature, or delta T, the little triangle T equation, we can figure out the change in temperature, and then we'll have all the pieces we need to put it into our heat equation. So let's start with that. So change in temperature. We always start with the final and we subtract the initial. So our final is 25.0 degrees Celsius. Our initial is 51.2 degrees Celsius. And so when we subtract those using significant figures rules, we know that they're both to the tenths place. So our answer also has to be to the tenths place. You can use a calculator, but I'm just going to move forward with writing it for quickness. 26.2 degrees Celsius, and that's negative because it cooled off, so it lost temperature essentially. Now we have all the pieces we need. So Q equals, the mass is 500.0 grams. Our C is 0.386 joules per gram times centimeters, and times the change in temperature, that's negative 26.2 degrees Celsius. Let me switch colors so we can see. So our grams will cancel, our degrees Celsius will cancel, and what we're going to be left with is just those joules. Now before we do that, let's look. We have 4 significant digits in this one, 3 in this one, and 3 in that one. So when we multiply, just so I can remember, I need to have 3 significant digits in my answer. All right, let me give myself a little bit more room to write the answer. So when I put those into the calculator, go ahead and open up the calculator so you can see that happen. So when I put those into the calculator, I have 500 times 0.386 times, I'm just going to put in 26.2 for simplicity and know that my answer is negative. So negative 5056.6, I can only keep 3 significant digits. So that's going to round me up to 506, because the 6 makes the 5 round up, and then this 6 is going to become a 0. And I don't even need to put a decimal because nothing after the decimal is significant. So that's negative 506, and then 0 in the ones place. And remember, our unit is joules. So that's how much we lost. And so the negative means that energy, heat is energy, and that's transferred. And so when the substance has negative heat, it means it lost energy. If it has positive heat, it means it gained energy. So in this case, negative joules means it lost energy. And makes sense, as it cools off, it's going to have less energy, because cooler things have less energy than warmer things. The hotter something is, the more molecules can move and the more energy it has. Okay, so let's look at the second one. There it is. All right, so this one, we can use our same 2 equations, but let's look and see what information we have first. To work on a 350-gram iron horseshoe, a blacksmith adds 59 kilojoules of energy to it. If the horseshoe started out at a temperature of 22 degrees Celsius, what is the final temperature? So I'm going to label the pieces our problem gave us so I can see what I have. And I'm also going to make a purposeful mistake so that you can see something to help in case you don't notice this later. So here's our mass, and here is our energy we're losing. So there's our Q, and then it gives us an initial temperature. So that's like our T. I'm just going to put I for initial. We don't have the change in temperature, but we do have our C that's already labeled. So we have most of the pieces of the heat equation, but what we really want is the final temperature. So this is what we want. But to get that, we're going to have to we're going to have to work towards there. So since the final temperature is what we want, we're going to need to, in the other one we started with the temperature equation because we had this and we had this, we wanted this one, and so we needed this. So to do that, we started with this second equation so that we could get our change in temperature to head towards the end. In this case, we want the final temperature. We don't have the change in temperature, and we do have the initial, but to get, so we have this, but to get this, we're going to need to use other stuff. And since you only know a few equations so far for this chapter, a few formulas, this is the one we're going to start with. We're going to use our Q formula because we know the mass, we know the specific heat capacity, and we know how much energy was added, our Q. That will give us our change in temperature. And once we have that, we can use that change in temperature to find the final temperature. Okay, so let's get started. Let's use our Q first. So Q equals MC change in T. So let's put in what we have. So we have 59 kilojoules. This is where my purposeful mistake is going to come in. 350 grams times 0.444. Did I really write that down? Yep, I did. Joules per grams times this. And then our change in temperature is actually what we're solving for, so I'm just going to put it in as a variable. Now, if I completed this or moved forward with it, you can see that I would need to rearrange this. And so I would need to change this around, and I could put the change in temperature. In fact, you might want to do that before you get started. So you might want to rearrange this. Think about multiplying both sides by, or dividing both sides by Q. Not by Q, by MC, to move that so that the temperature is by itself. So change in temperature equals the Q. So far I've just flipped the equation around, but the MC is not going to be with the T anymore. I'm putting it on the bottom. So if you want, you can do that first, and that might actually be more helpful. If I do that, you're going to see that I'm going to end up with the Q on the top, which is this one, and on the bottom I'm going to end up with these two, which means that I'll have kJ on the top and grams times joules per gram times degrees Celsius on the bottom. Top, bottom, within the denominator. But I can't cancel this one and this one because one is kilojoules and one is joules. And so what I need to do is, before I even start this, I need to recognize what units I have, because my units have to cancel. So if you had kind of put in the 59 and included all of your units in the problem and worked all the way through it and got to the point where you're canceling your units out and you realize, wait, KJ and J do not cancel together, you would know that you needed to go back and fix it. So that's one of the reasons that that it's very good to always write your units in. So let's erase this and let's fix it. In fact, actually, I think I'm going to erase this whole little thing because I would rather work with an already rearranged equation than have to rearrange it with lots of numbers. All right, so we're going to take this and we're going to convert from 50, oops, I should put that on the other side, 59 kJ to just J. So kilojoules to joules, what's our relationship there? Kilo means 1,000 of something, so 1 kilojoule is 1,000 joules. So you can either do, I'm going to scoot this over for just a second. You can either just take the 59 and move the number, or you can use that relationship and put kilojoules on the bottom and joules on the top, and then use this to put those numbers in. So 1 times 1,000, so that you know whether you need to. Sometimes it gets confusing for some people. Do I divide by 1,000? Do I multiply by 1,000? So this will help make sure that you know which one you're doing. So we're going to multiply by 1,000 to figure out how many joules we have. So we have 59,000 joules. So 59,000 joules. All right, so let me erase this extra stuff so it doesn't get in my way later. And hopefully you saw enough to see how I got that number. All right, so now we're ready to put it into the problem, and we're going to put everything in our altered equation or rearranged equation. So Q on the top, that is our number that we just fixed, so 59,000, just plain joules. And on the bottom, the mass is 350 grams. And I'm using this equation right here to help me stay on track. And then my C they gave me 0.444, and the unit is joules on the top and grams times Celsius on the bottom. Let's start canceling our units first to make sure we know what we're doing. We're going to focus on just the bottom. You can like cover the 59,000 joules with your hand if you need to see it, and just imagine just this part as if it weren't under a fraction. It's just plain. So the grams on the, out of a fraction, and this gram is underneath a fraction, so those two will cancel together. Now, uncover the 59,000 with your hand. Notice that we have a joule down here and a joule down here, one on top of the fraction, one on the bottom of the fraction. They can cancel. The Celsius one gets a little tricky. There's nothing to cancel it with, and we know we want our units to be in Celsius. But if you think about it, if you have something on, here's a fraction, and there's something up here, and then you have another fraction on the bottom with something, I'm going to put some letters, X and Y. Let's call this a B, since it kind of looks like a B. If you have something like this is really like saying like B divided by X over Y. And when we divide fractions, what ends up happening is it's like B times Y over X. And so that thing that was on the bottom of a fraction, that's also a fraction that's on the bottom, like the fraction is in the denominator, and then this Y is in the denominator of that fraction. I'm saying fraction of too many times, but it's the bottom of a fraction. And so that thing is going to end up on top, like out of fraction. And so that degree Celsius that's over here that we were just looking at is actually, that unit is going to be not on a fraction at all. Kind of like two negatives make a positive. You stick a denominator in the denominator and it becomes a numerator. Okay, so now we can plug it in. Before we plug it in, let's look at our significant figures. So the 59,000 has 2, 350 has 2, and the 0.444 has 3. And so 2 is our lowest number. I'm just going to put it in a blobby cloud so we know it's not an answer to anything. That's just how many significant digits that I need to have when I'm done working with this. So let's get our calculator out. So we have 59,000 divided by, and I'm going to put the other two numbers on the bottom of my fraction in parentheses together because I'm multiplying them together on the bottom of the fraction, and then I'm taking that number and dividing it into 59,000. So 350 times 0.444. All right, so I have 379.665 blah, blah, blah. But I can only keep, remember in our little green bubble, 2 significant figures, which means I can only keep these 2. So if I round it up, I'm going to get 380. So I have 380 degrees Celsius. Now, does that answer my question? What was my question? What is the final temperature? No, that does not answer my question. That just gave me the change in temperature. That's what that number gave me. And what was I going to do with the change in temperature? I now have it. I can now find the final temperature, which is what it's going for. So we don't get confused. Let me change color and squeeze it up a little bit. So we have, I'm going to put this over to the side because I'm going to rearrange this one. So change in temperature, well, that's not at all proportional. Change in temperature equals, I'm going to put T of F minus T of I. That way I don't have to write the whole words. I want this one. So this one needs to be by itself. Use some algebra. How do I get it by itself? I can add the initial temperature to both sides, and then it goes away over here. So let's use that equation. So change in temperature plus the initial temperature will give us our final temperature. So our change in temperature was here. So that's 380 degrees Celsius. And then our initial temperature was given in the problem right here. It's 22 degrees Celsius. And let's add those together. So when we add those together, we get 402 degrees Celsius. But let's look at significant digits just to make sure that we don't need to do anything. So we have 2 and 2. So again, we have 2 significant figures, which means we can only keep these 2 decimal places. The ones place has to go away. So when we round this, it would be 400. But the problem is that now it looks like I only have 1 significant figure, because we know those zeros only matter if they come after, like if we had a decimal in there to indicate that they're also important. And so we need to find a way to make sure that we know that these two are important, but this one is not. So what we're going to do is we're going to convert this into scientific notation. So scientific notation tells us that we need to have one thing in front of the decimal. So we're going to move our decimal there, and it's going to be times 10 to the something. So let's go back to, well, we can really use either one of these. Put a decimal here, and we're moving it this way. How many times did we move it that way? 2 times. So that's times 2. Is it correct that the 2 is positive? Yes, because if we took 4 and multiplied it out by 10 squared, which is 100, we get 400, which is what we want. So, and this is degrees Celsius. Sorry, I had to kind of squeeze that in because I ran out of room. So that is our final temperatures, 4.0 times 10 to the second degrees Celsius. And we have to write it that way so that our significant figures work out and are obvious that there are 2.